In Module 9, we have seen joint strength using the analytical approach. In this module, Module 10, we are going to predict the joint strength using numerical methods.
Joint design can be made using analytical models. That's when the differential equations are not too difficult and they have a mathematical direct solution. But in many cases, in most cases actually, for a complicated geometry, for a complicated constitutive model for the adhesive, there are too many differential equations to solve and you need an approximate method. The most commonly used is the finite element method. So commercial softwares are used, and the technique consists in cutting the structure in very small elements, as indicated here. The objective of the game, I can say that, is to determine the displacements at the nodes of the elements. This is done in general by minimizing the energy of the system, and this process of minimization generates a system of equations with the matricial form expressed here. K is the stiffness matrix, D is a vector with the displacements of the nodes, and R are the external forces applied. So if you solve this system of equation, then you get D, the displacements of the nodes. Once you have the displacements of the nodes, you can get the strain. Once you have the strain, you can get the stress all over your structure for any geometry and any type of material. That's a really powerful tool. The problem is that parametric studies are more difficult because every time you change the geometry, you need to construct a new model. But let's look at the single lap joint, which is the joint most commonly used in adhesive bonding. You have here the stress distribution for the case where you have a single lap joint loaded like this, and as we have seen with Volkersen, for example, the stress is something like this, right? You have the black dotted line indicated here. If you do this with a finite element model, you might not get it at first. You might be here with this red line because you are using a too coarse mesh. If it's too coarse, then you might not capture the gradient of stress that occurs at the end of the overlap. So what you need to do is refine, especially where you have gradients, especially at the ends of the overlap, until you have convergence with the real stress distribution. So this is a very common exercise when you use finite element method, is to do a merge conversion to make sure that really you are obtaining the right stress. This is especially important where you have gradients of stress. The problem is that you have singularities in single lap joints, and you have the most important ones indicated here, here and here. What that means is that as you refine the mesh, the stress tends to infinity, and there is no limit. The finer, the higher the stress. Of course, this is not suitable. If you want, in the next phase, apply a suitable failure criterion based on the stress level, because it will depend on the mesh size that you use. So you have a problem here to solve. One way to solve this is to use damage mechanics and more precisely cohesive zone modeling. This is a technique or a type of element that is used nowadays by everybody that works with adhesive bonding. So for the adhesive, you use cohesive elements, and associated to these cohesive elements, you have a cohesive law, which is a law which relates the stress to the displacement of these two nodes, or these, anywhere in the overlap where you have cohesive elements. And let's look now at this cohesive law. Let's analyze this cohesive law. So initially, when you load the joint, this will cause also loading in your cohesive element, and you follow this line. When you reach a critical stress, then you start to have damage. Imagine that you used only a continuum mechanics approach. If you use this limit of stress, then the joint would fail. That's what we use when we use Volkersen or Line-Rice, and when we reach the failure strength of the adhesive, boom, it fails. There is no more after that. However, in this case, we also take into account fracture mechanics concepts. It's a mixed approach where we use continuum mechanics and fracture mechanics. So it's not failed yet. It starts to be damaged, and it follows now this line. Imagine you follow this line and you unload the specimen. You unload, you follow this path. If you load again, you follow this path. So the stiffness is lower. You moved from this stiffness undamaged to this stiffness that is damaged. Okay? So there is a damage of the cohesive element. And if you further load the joint, then you follow this path until you reach this point. When you reach this point, then you have a disbond here. Boom, it will disbond, because it's the case where the energy here is equal to the fracture energy of the adhesive, and then you have a disbond. You can still carry on loading, and this will then happen to this element, etc., etc. But it's nice because you combine continuum mechanics, fracture mechanics, and you can predict not only the point where you have initial damage, but also the point where you have crack initiation and propagation, which is fracture mechanics, of course. So really very powerful tool which can give you the whole picture, not only when it starts to fail, but the complete failure process. All right? You have here in this slide an image or a model of what you can obtain when you use cohesive elements in a DCB. Do you remember that fracture mechanics test that you load in mode 1 like this? We put a cohesive element or cohesive elements along the bone line, and you get the failure process in the DCB. All right?
In this demonstration, we will use the Single Lab Joint Designer, a modeling tool for Abacus CA. This tool has been developed by Adhesiove's Advanced Joining Processes unit. When we start developing a simulation, there are several steps to take, starting with designing our parts, meshing them, applying boundary conditions, and so on. This tool will allow us to do all of that, but in a much simpler way, using these input windows. Initially, we must define the dimensions of our joint we want to simulate. For this, we need to consider both the substrate and the adhesive dimensions. Then, in terms of materials, we can choose both the substrates and the adhesive materials using this window. We can perform an analysis of dissimilar or similar joints by selecting the adequate materials. For each substrate, we can define its behavior as elastic or plastic, and the same is applied for the adhesive. In this case, we will use cohesive zone modeling, which defines cohesive elements along the overlap length, which will allow us to capture the failure load and mechanism. In terms of mesh, we will divide our dominium into small subdivisions having larger and smaller elements, according to what is needed. This will be detailed later. Finally, the last step is applying boundary conditions and defining some simulation details. For this example, a displacement of 1.5 mm is applied to the end of our joint, while the other side is fixed. We can define our job or simulation name and the amount of CPUs that we want to use. Now we can generate our model and submit the simulation. While we wait for the simulation to be finished, we can explore the meshing environment in Abacus, and for that we can go to the mesh module. Adhesive joints usually prefer a finer mesh near the adhesive, especially near the stress concentration points, in order to better capture the stress field and failure mechanisms. However, the rest of the model doesn't require such finer meshes, hence a coarser mesh is used in non-critical areas in order to save computational time. With this explained, now we can go back to the Single Lab Joint Designer module and visualize the results since our simulation is now finished. Here we can analyze several parameters such as the von Mises stress and use animations to see our joint failing over time. Another parameter that we can analyze is the S-tag, which defines the damage accumulation on the adhesive layer from 0 to 1. We can see through a graded scale that as the joint is being tested, the damage in red is being accumulated while the joint fails progressively. And with that we concluded the tutorial.
So, in terms of joint design Again, you have the analytical models. It's very nice for an immediate answer. If you want something more elaborate, you can use finite elements. And if you want to avoid the problem of the merge of the singularity when you use continuum mechanics, you can use cohesive zone elements. They are not that sensitive to the mesh density because it's not a point stress, it's more a stress that is averaged over an area, and it's a very powerful tool that combines continuum mechanics and fracture mechanics that can give you the whole failure process of the joint.